So archaeologists begin with the law of superposition. With that, we know that the story more or less begins at the bottom, and the rest of the story is contained in the layers above. So we're going to take a look at Gatecliff Rockshelter as an example to see how this is used in action. This site, which was discovered by one of your textbook authors, David Hurst Thomas, has a 40-foot stratigraphic profile spanning about 7,000 years. So in other words, the deposits that they excavated are over 40 feet thick, and there's a lot of stratigraphy recorded in the profile. When I say profile, what I mean is typically it's a drawing of sort of the side view. After you're done excavating, you're going to have this wall of dirt on one side of your excavation, and when you draw that, we call that the profile. Or even if you don't draw it, just looking at it, that's your profile. So the Gatecliff sediments, just like any other archaeological site, these sediments result from both natural processes and human behavior. And it's the goal of the geoarchaeologist to try to figure out which of these layers are cultural and which are natural. So let's take a look at the master profile, the master stratigraphic profile from Gatecliff. This is showing layers 1 to 33 out of 56 total that were recorded for the whole site. The geoarchaeologist has numbered the layers sequentially down the left side and put the calibrated calendar ages on the right. In the master stratigraphic profile, the thin dark levels are the ones that they had inferred resulted from human activity. And this is inferred from the type of things that are recovered from the site. How do they know that they're cultural? Well, they find charcoal, ash, stone tools, grinding slabs, food remains. Occasionally they find basketry. The site has very good preservation. So they infer that these are cultural levels by the things that they find in them. At Gatecliff there were 16 of these cultural strata. But most of the strata here are geological in origin rather than cultural. That is, they were formed through natural processes. Stratum 8, for example, right here, consists of upward finding alluvial sediments. Now, alluvial sediments form when floodwaters settle. So we're talking about sediments that are entrained in moving water. When you're talking about floodwaters, typically you're talking about high velocity water movement. At least in this part of the world you are. And when the there's an ephemeral stream outside of Gatecliff Rockshelter. And when that stream floods, if the waters get high enough to load up into the rock shelter, then they are moving rapidly. Rapidly moving water carries lots of different sizes of particles, from pebbles to sands to silts to clays. In fact, sometimes they can even carry boulders, depending on the size of the stream and the velocity of the water. But as the waters slow down, as the flood recedes, if you will, the waters begin to slow down, the first thing to fall out of the water is going to be the heaviest particles. So as the water slows, the heaviest particles drop out first. And it's the light particles that stay in the water. And this pretty much continues all the way until the water is gone, or ponded even. If the water recedes while it's still moving, then it might stop depositing at silts, say, for example, or sands. But if the water stops as a pond in the cave, then you can actually have clays, which will settle out of the water last. And you can simulate this by getting a bucket of mixed dirt at home I guess, and then stirring it up, and you'll see that the heaviest stuff sinks to the bottom, and then the sands, and then the silts, and the clay will stay floating in the water for days. And if you leave it long enough, the clays will then fall out. Well, if you can imagine cutting that in half, that's how an archaeologist or a geoarchaeologist can identify a deposit as having been created by receding floodwaters. So as part of understanding the history of the cave, the geoarchaeologist comes out and can identify which of these layers were made by people and which of these layers are made by nature. Some other types of deposits that you come across other than alluvial, you have something we call Aeolian deposits or Eolian deposits. Those are deposited through the action of wind. So sand dunes, for example, are a good indicator of our type of Aeolian deposit. Aeolian deposits don't have to be dunes. I mean, you have to have pretty strong winds to carry sand around. But silts and clays can be carried in the wind also. Typically when you have Aeolian deposits, though, you're looking at some place that's been devegetated to some extent. So you can tell a little bit about the climate history. If you have a place that has Aeolian deposits in it, you might be able to infer that this was a drier time period when there was less vegetation cover. Obviously, if you have grass covering everything, you're not going to have a whole lot of sediments being entrained. But whenever you have erosion, whenever you have sediments that are exposed, you can have Aeolian deposits. And then you have cultural deposits that are deposited primarily through the actions of people. There is a lot of other types of deposits we could talk about, but these are the ones that are pertinent to our story here at Gatecliff. This is a photograph down near the bottom of Gatecliff stratigraphy. This is at the 40th foot level, if you will. Most of the stratigraphy at Gatecliff is unique. So the strata that are identified, those 56 strata, most of those are only found at Gatecliff Rockshelter. They're not going to be found in the next rock shelter over. You can't correlate them because they formed only in the site. Occasionally, though, you can find a strata that turns up in more than one site. Now, an example might be if there were 2 or 3 rock shelters in this area and there was a particularly big flood that got them all, you might be able to correlate those floods, see that flood deposit in each of the rock shelters. But they didn't see anything like that at Gatecliff. But what they did find, near the bottom, at stratum 55, they found a layer that contained volcanic ash. Now, volcanic ash obviously doesn't form inside of a cave. It could be thought of as an Aeolian deposit. But what happens with volcanic ash is usually chemically distinguishable. So 2 different volcanic eruptions will have different chemical signatures. Chemistry being determined by the sorts of rock and that was being put out by the volcanic eruption. So see, the last big eruption in the United States that I can recall would be Mount St. Helens. And Mount St. Helens ash is all over the Pacific Northwest. And you can go out there and you can find that ash buried in the dirt occasionally, and you can identify it, or scientists could identify it as having come from the Mount St. Helens eruption. Well, this ash in a Gatecliff shelter was identified as coming from Mount Mazama, which is an eruption that they know occurred about 6,900 years ago, 6,900 BP. They dated that through the argon-argon method. They didn't have to date it here through the argon-argon method. It's been dated elsewhere through the argon-argon method. Here, they only had to find it and be able to chemically identify it as being the Mazama ash. So we call that kind of marker horizon a marker bed or a marker horizon. Your textbook calls it a marker bed. Bed is a geological term that refers to a single stratigraphic layer, sort of a generic term. I don't use the term much. I usually will call it a stratum, or a horizon. But your textbook calls it a marker bed. These are fairly handy. With a marker bed, your textbook definition, an easily identified geologic layer whose age has been independently confirmed at numerous locations and whose presence can therefore be used to date archaeological and geological sediments. So this Mazama ash can be found at a number of rock shelter sites throughout the region. I probably should have mentioned what part of the world we're looking in, actually. It would have been a good idea to give you an introduction to Gatecliff Rockshelter. Let me take a step back for a second. Gatecliff Rockshelter is located in the American Southwest, the Great Basin area, which is basically it's predominated by Nevada, but also extends a little bit up into Utah and other neighboring states. But primarily we're talking about Nevada. Now, during the Ice Age, there was a large lake that covered much of the American Southwest. This area where the lake is called Great Basin. So if you ever hear the term Great Basin being used, it refers to this area that was a large lake during the Ice Age. Well, at the end of the Ice Age, this lake more or less dried up, creating the place where most of these deserts are out there. In the earliest parts of the Holocene, so the Holocene is this period that occurs after the Pleistocene, after it dries up. In the earliest parts of the Holocene, that lake is still there, it's just getting smaller. And these caves, are rock shelters, if you will, are located all along the edge of the Great Basin. A lot of them may have been formed through water activity during the high stand of the ancient Pleistocene lakes. But as those rock shelters emptied out and people began moving into the New World around 13,000, 14,000 years ago, or 12,000 or 11,000, they began occupying these rock shelters. That's the part of the world we're in. So with this marker horizon, if you find this marker horizon, you know that anything beneath it is older than 7,000 years. So that puts it as a pretty old archaeological site in the United States. We're looking at what they call a Paleo-Indian site. And the Paleo-Indians we refer to as the earliest occupants of the Americas. So that makes this Mazama marker horizon pretty important. You can have other kinds of marker horizons. Soils can make marker horizons. Now, soils are not, strictly speaking, strata. Right? Soils form on strata. They form on sediments. Let's just use the term sediment to refer to unaltered parent material. It's just something. It could be sand, it could be clay, it could be silt, it could be gravels, but it's not a soil. Soils form on stable surfaces. Soils are made by the contribution of organic matter and rodent activity and trees and time and water. And so soils become chemically altered, if you will. They're chemically altered sediments. And we have terms that we use to describe these in archaeology and geology. The uppermost part of a soil is the A horizon. The A horizon is usually the horizon that is most impacted by rodent and burrowing activity. It's defined here as the upper part of a soil where active organic and mechanical decomposition of geological and organic material occurs. It's typically the darkest part of a soil horizon. If you've ever cut away the soil, you can usually see that it's darkest at the surface. Not always, it just depends on the parent material, but quite often it's darkest at the surface. But we then have below that a B horizon, which is the layer found below the A horizon where clays accumulate that are transported downward by water. So one of the alterations that takes place through rainfall is the transport of clays and minerals from the A horizon down into the B horizon. Things that are easily dissolved, chemicals that are easily dissolved will also move downward in the soil profile, potassium, salts and whatnot. So you can have salt accumulations down in the B horizon. This usually is not quite as dark as the A horizon. And I'm terribly simplifying this. But you can guess what's down next is the C horizon. And the C horizon, usually we call this unaltered parent material, or you might say slightly altered parent material. It's the sediments on which the soil formed. Well, anytime you have stability in a geological area, you're going to have some soil development. In some places, the soil development can be very slow. Honestly, it's dependent on how much water percolates through the soil. So if you have a really dry place, such as a desert, or if you have, or the Arctic, you're not going to have a lot of soil development. And the places where you have the most soil development are places that have a lot of rainfall or a lot of organic input on an annual basis, like a grassland, for example. Grasslands grow tons of biomass on an annual basis, much of which dies and is ground up and goes into the soil profile. So you have a tremendous amount of organic inputs, plus you have water, sometimes floodwaters. So grasslands, you get these really thick, deep soils. They're usually very black and rich on top. If any of you are from Kansas or North Texas, the southern Great Plains, you might know what I'm talking about with these really dark soils. Well, a geoarchaeologist has to be trained in this sort of thing because soils can become buried as well. And when they become buried, well, we call them paleosols, but let me give you an example of a soil. Here is let me put this all out here again, same definitions. Here's your A horizon at the top. This is a typical Texas profile, not along the Gulf Coast, but perhaps around in Piney Woods type area where you have kind of a sandy sediment on top there. And then you have that brown, dark brown on the top, and then you have this orangish red down there on the bottom. Well, actually almost at the bottom, and then below that you have this other stuff that's kind of a gravelly material. That is your unaltered parent material. Above it you have altered sediments. You've got essentially two B horizons in this particular profile, and then you have an A horizon at the top. The A horizon is brown because of the addition of organic matter. If you could somehow wash it and take out all the organic matter, it would look a lot like the B horizon. It would be tannish white like that. So this is not an indication of human activity. So why do we need to know it? Because whenever there's a surface, it means people could be living on it. So you find these paleosols, for example, like this one, along the Brazos River, called the Asa paleosol. This paleosol, the term paleosol, it refers to a buried soil. I don't think that term is given in your textbook, but it ought to be. It's a real common term used in archaeology. A lot of archaeological sites found on this paleosol. It's a marker horizon. It can be found all up and down the Brazos River. It indicates a period of stability. And during that stable period, a rather well-developed soil occurs on a grassland, at which time there were bison and whatnot roaming around. So right here or right up there, I should say, right up the Brazos River, you really had the southern Great Plains extending far down into this region between 1,000 and 3,000 years ago. We don't have nearly as much of this going on anymore. There's been a lot of deposition on top of this and that's all alluvial deposits. Sometimes people call this more specifically, they'll refer to as a fluvial deposit, but let's not get into that. So a paleosol is a type of marker horizon, and it's very helpful in archaeology because once you know how old the marker horizon is, as soon as you begin excavating there, you can have an idea of how old the archaeological site is that you're working with. I'd like to sum up, though, with a discussion of rock shelters in general and how they form and how a geoarchaeologist can help contribute to understanding what's going on. You will start with figure A, I guess, or picture A. And this is taken out of your textbook, so you can refer to it there if you'd like. But A shows kind of a side view of what a rock shelter might look like with some sort of sediment outside the rock shelter. That's the orange-looking deposit. They don't tell us what it's made out of. Let's just say that it's alluvial deposit, that it's some kind of sands that are deposited out in front of the rock shelter. At time, let's just say, for argument's sake, that people create an archaeological site out there just outside the rock shelter. Let's just say they build a fire out there, they're doing cooking or whatnot, and so there's an archaeological site on that surface there in picture A. Fast forward to picture B. Some amount of time has passed. The rock shelter has started to recede because this is what happens with rock shelters, is that you have erosion at the lip of the cave. The water line begins moving back as erosion occurs. In this case, you've got rooffall. The rooffall lands directly on the oldest sediments. And then you have additional alluvial deposits that can come in from floodwaters, and they deposit right over that rooffall. Now, if people are occupying the surface just outside the cave, they're actually going to be a little bit closer to the, a little bit farther to the right or closer to the back of the cave. You can also see that the stratigraphy has gotten a little more complex because you've got these big boulders that are cross-cutting two or more strata at this time. Then you have C. You have additional rooffall falling on the alluvial deposits in green. And then on top of that, you have colluvial deposits indicated by that light orange. Now, colluvium, this is your gravity deposits. This is just a rooffall, I guess, would be technically a type of colluvium, but typically when we talk about colluvium, we're talking about sediments migrating downhill. It takes a long time. It can be mudslides, it can be landslides, but it can also just be day-to-day gravity creep. You know, over 200 or 300 years, sediments move downhill. A geoarchaeologist can easily tell the difference between fluvial deposits and colluvial deposits because the fluvial or alluvial deposits, rather, are well sorted. As I mentioned before, as the speed of the water slows down, the sediments get well sorted from coarsest at the bottom to finest at the top. Gravity deposits are all jumbled up, and they tend to be angular. If you look at an alluvial deposit microscopically, they're all rounded because they've been carried by water, whereas colluvium often is broken and crumbled, and it's all angular deposits, so it's easy to identify. But nonetheless, it's over this colluvial deposit, and you find a lot of colluvial deposits in rock shelters because the rock shelter itself is disintegrating. If you have another flood, you'll see they've got this alluvial deposit now, and it's actually inside the, it's being sort of captured inside the lip of the cave, if you will. The colluvial deposits are outside the front of the cave, and the alluvium is deposited there on the inside, probably from some kind of ponding activities. There's a flood, the water ponds in there, the water eventually evaporates, leaving you with that colluvial deposit on the inside. After this, you've got additional colluvium that overlies the alluvial deposit, some additional rooffall, and last but not least, you've got some Aeolian deposit. This is just a sort of a model of a hypothetical rock shelter filling with colluvial and Eolian sediments and rooffall and alluvium. You can see, though, that the stratigraphy is all of a sudden quite complicated. In an absolute sense, you have colluvium that is higher in elevation than, or you could almost have a reverse stratigraphy. See that yellow, the yellow deposit there, which is alluvium supposedly, is overlying that light orange colluvium. But you'll see, because the colluvium wasn't deposited flat, it was actually made a little hill outside the cave, that in sort of absolute terms, there are parts of the colluvium, even though it's older than the alluvium, it's actually above the level of the alluvium. This is the reason that when you are excavating, you have to be very, very careful about recording all of your deposits and where they are, and identifying all of the different geological events. Because you can date these events. If we were to go back to our first couple of slides that showed the picture of Gatecliff Rockshelter with the numbers on the left and the dates on the right. Well, these deposits have an age range. You know, they're forming at some point in the past. And when you find archaeological sites either on them or in them, you use those dates on the deposits to actually date the archaeological site. Remember, this is when we were talking about dating. What are you actually dating? Well, if you find dispersed charcoal in a colluvial deposit and you date it, you're dating the age of the deposit at best. And if you find an archaeological site in that deposit, you can say that that archaeological site is probably from that time period, or it could be older. Not to make it too complicated, but how could it be older than the deposits that it's in? Because you could have an old deposit that is eroded into, eroded and deposited with a new deposit. We'll get to that when we talk about reverse stratigraphy, but this can be quite complicated. So the job of the archaeologist is, they've got their work cut out for them. There's another trend, though, that I want you to notice here, and that is, let's just suppose you show up at time D. Let's say time D is now, and you arrive at this place, and there's a nice archaeological site back up there on the colluvial and Aeolian deposits. You've got preserved basketry and stone tools and ash and charcoal, and you're really excited as an archaeologist. So you put a test pit in right there where it says Aeolian deposit, and you go straight and you excavate straight down. You hit bedrock after a couple of meters, and you go through Aeolian, colluvium, and alluvial deposits. Let's say you expand it out a little bit because you want to get the entire water line. So you put another test pit in at that joining juncture of colluvial deposit and Aeolian deposit. And you go straight down, you hit some rooffall, and then you hit some alluvium, then you get into some colluvium. Okay? But you're not working at all out in the old soil, in the oldest surface that was way out in front of the cave in antiquity. Why aren't you working out there? Well, if you don't understand how rock shelters form, you might think that the archaeological site should be in the rock shelter or just out in front of the rock shelter. The thing is, you have to realize that that rock shelter may have, 7,000 years ago, extended much further out than it is today. And the oldest site is not going to be in the rock shelter or even at the waterline of the rock shelter, but perhaps 10, 15 feet or meters out in front of the rock shelter. And this is exactly what you have going on at Gatecliff. I did not put any more slides of Gatecliff in this presentation. There's very few that are available on the internet. I took a look and I found about 4 or 5 that show the sort of the depth of these deposits and how big they are. They had to build, there's 40 feet of deposits. They had to build staircases and landings to get out. They had to transport their dirt up these staircases, sometimes in buckets on pulley systems and do all their screening outside. It's a massive undertaking. But these nicely layered deposits that they had at Gatecliff allowed them to get a really good handle on the stratigraphy. And consequently, they were able to get a good handle on how the archaeological site changed through time. They were able to get an idea of how the climate changed through time, because when you have those Aeolian deposits, you tend to have drier climates and less vegetation. Obviously, the alluvial deposits and the floodwaters can indicate wetter times or periods of more rainfall. There's a lot you can learn from these deposits. The rooffall tends to happen in winter precipitation because of freezing and thawing. There's a lot of things that go on there. So they got a good idea of the climate history as well as the changing cultural history. And we haven't even discussed the artifacts or the things they found and how their way of life may have changed through time. We're really just talking now about how a geoarchaeological perspective can help you understand what it is you're dealing with. In the next lecture, I will discuss more complicated stratigraphy. For example, the so-called reverse stratigraphy that they found at Gatecliff, which we'll use as an example. It's discussed in your textbook. What I'll do is I'll be putting this lecture online. I'll update it with a few more pictures from Gatecliff Rockshelter so you can see the extent of the work that they did. So take a look for that online. Friday's lecture